Started. I'm Charlie Smith, the Executive Director of ESIG, and I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. I also serve in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with the research agenda for the system operators. More information on the GPST can be found at globalpst.org. We've been quite busy this year in spite of the COVID, having just finished up our fall technical workshop in October and preparing for the new year when we hope to be back in person again. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we've moved to the Slido platform, and we're asking you to ask your questions through Slido. So go to slido.com and enter ESIG16 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today's topic will be on redefining resource adequacy. After the events in California a year ago, in Texas this past February, and other system operators around the globe, this has become a very hot topic. The webinar will be presented by Derek Stenclik, who is a founding partner at Telos Energy, a power systems engineering consulting firm. Derek is currently leading a resource adequacy project on behalf of ESIG. He was with GE Energy Consulting prior to starting Telos and has a decade of experience helping clients across the industry accelerate the transition to clean energy systems. I've known Derek for most of this time, and I feel very fortunate to have him here with us today. On a personal note, as I like to do, I took a look on LinkedIn last night to check our mutual connections, and I found out that we have 167, which is about 50 more than last year at the same time when he gave our first resource adequacy webinar. So I take that to mean that there's growing interest in RA, Derek. I think we're in the right place at the right time. But I have to tell you, he knows a lot more about resource adequacy than I do. I greatly value Derek's contributions to ESIG in the industry, and I look forward to what he has to say. Derek will expand on the principles outlined in the ESIG white paper released in August, Resource Adequacy for Modern Power Systems, and will further elaborate on recommendations for improved resource adequacy metrics and future options for the planning reserve margin. Just a short reminder once again to use Slido at slido.com with the event code of ESIG16 to ask your questions. Okay, without any further ado, let's go ahead and get started. Derek, I'll now turn it over to you.
Thank you, Charlie, and thank you everyone else for joining today. I'm really looking forward to another webinar with ESIG and talking about resource adequacy. As Charlie just mentioned, about this time last year, was able to share the initial findings from the ESIG project on redefining resource adequacy. Since then, a lot of you have probably seen me at other ESIG events, like both the spring and fall workshop, and have probably seen the white paper we just put out. So obviously, a lot of work has been done in the past year. Looking forward to briefing all of you on that. And also want to make sure if there's folks joining that have been to some of those more recent webinars through the fall or spring technical workshops, do want to make sure that we keep it interesting. So added quite a bit of content, quite a few ideas. Really, what I want to talk to you today is not necessarily what's been done in the report we just put out, although I'll highlight that, but want to talk about what still needs to be done. What are the unanswered questions? What does the industry need to be thinking about? So with that, I'll jump in. Do want to acknowledge kind of Charlie and the rest of the ESIG team. This has been a project that we've done on behalf of the Redefining Resource Adequacy Task Force, so a group of several folks, industry experts in resource adequacy, and then as well as coordinating amongst the GPST, so the Global Power System Transformation Consortium that Charlie mentioned. And you can see several links off to the right, and obviously this presentation will be posted on the ESIG website, and you can go through and check out the white papers that we recently put out on these topics. And most notably, recently we put out the policy brief there at the bottom. And so this was timed to coincide with the COP26 summit in Glasgow, with the intent to put a very clear and concise primer on how resource adequacy starts to influence public policy decisions. And really, as we start to think about public policy goals of 100% by 2030 or 100% by 2040, what does resource adequacy mean in that context, and how might we think about resource adequacy in a policy framework? So that just recently came out last month, so I want to point you to that. We also have a C-grade paper coming out that we'll be submitting in the next few weeks on evolving metrics. And then again, next steps, want to talk to you today about potential topics for 2022, whether it's ESIG to take on or other folks in the industry. I know there's a lot of different working groups and consortiums tackling RA across the country and globally right now. So today, wanted to walk through 4 different topics with all of you, and certainly leave some time for question and answer. So the first is a quick summary of those principles of resource adequacy. Again, many of you that are joining that have participated in previous webinars have seen that, so we'll hit that at a high level, but again, set the groundwork for the rest of the presentation. The second topic is around gaps in weather modeling and assumptions, and really this is a clear next step for follow-on research. The third is around evolving resource adequacy metrics, and then lastly on some pitfalls and opportunities on capacity accreditation. So what do we need to think about in the way we stack resources in their ability to provide or improve resource adequacy? So again, Charlie mentioned right off the bat, recent events in the US, there's also been others that have occurred globally in the past year. One was in California in August 2020, 2 consecutive days of load shedding. In Texas, obviously, nobody missed this one, a really large 3+ days of continuous load shedding, probably one of the largest resource adequacy events in recent history. So what I want to do is talk about those 2 events, obviously very different, but want to talk about what can we learn from both of them. And the first is not all shortfalls are alike. These 2 events were very different. In the California context, just a couple hours across 2 consecutive days. In the Texas event, systemic load shedding for 72+ hours, a huge portion of the overall load. So the underlying events, when we do have a shortfall, what does that mean? We need to think about how we characterize events differently and make sure that we can characterize the size, frequency, duration, and timing of events. That's something you'll hear multiple times today. The second is risk is shifting. So in both events, the resource adequacy risk was outside of the conventional peak load period. And this is very notable. In California, it was several hours after the gross peak load and occurred during the net peak, or the peak after the renewables, so during the evening period after the sunset. Load was lower, but the resources available were different. And that's notable. It's also occurred during a peak load that was very different, relatively modest if you look back at the last 10 years of load in California. So that's something to consider. On the Texas side, conventionally, folks think of Texas as a summer peaking system, which it is, and generally risk and scarcity events are occurring in those really hot summer snaps in Texas. But it occurred in the winter, and so again, risk, reliability, peak reliability risk, no longer just correlated with peak load. That shift is occurring. The third, something that I will talk about extensively today, is weather is the primary and most important driver for resource adequacy. It always has been, because weather has always influenced the load, but I think it's becoming increasingly important because weather is also affecting our supply side resources, both with wind and solar, but also with, as we start to, not only shift to variable renewables, but the system has become significantly more natural gas centric over the past several years. And so there's an underlying implication there for weather effects on the gas system. And then lastly, resource sharing. So both of these events showed disparate views on the capabilities for resource sharing. I think in the California example, about 10 gigawatts of imports occurred during the peak load event, and certainly very helpful in that example. In the Texas event, as a mostly islanded system with limited capability to import, certainly no imports in that context. So I think, again, just wanted to frame that. It's nice to start with real life resource adequacy events to frame this discussion. And so why is resource adequacy challenged, or why is it broken? In the white paper, we came up with two fundamental drivers. One was around chronology, the other on correlation. So on chronology, there's a need to look at things not only across every hour of the year, but actually as the system operates hour to hour. And so to some extent, modeling tools or methods in the resource adequacy space haven't necessarily introduced this concept that hours are sequentially linked. And so the need to do our analysis sequentially to capture not only the variable renewables, but more importantly, the energy storage and load flexibility on the system. And this, again, will become increasingly important. And then on the correlation side, resource adequacy analysis in general, or historically, made the assumption that we had all these forced outages on the supply side, the forced outages on the generators, and those were uncorrelated events. You had random occurrences that would take generators out of service, and you did a lot of probabilistic analysis to say, what's the likelihood of multiple generators going down at the same time for uncorrelated reasons? Fundamentally, what catches the system short is when we start to see correlating or cascading events or root cause failures. And this predominantly driven by the weather, forcing combined outages, again, not just low wind and solar production, but also combined outages on the natural gas system and other thermal systems, as cold snaps can affect the reliability of our system. And then lastly, as we shift towards more modular technology, inverter-based resources, wind, solar storage, the likelihood of us losing a large plant simultaneously diminishes. And so there's less emphasis to really need to look at the probability of these large discrete outages over time, and again, more emphasis needed on the correlation side. And then obviously climate trends just further exacerbate the correlation challenge. So those are the two fundamental drivers. We took those and we took a step back and said, what are 6 principles for resource adequacy for modern power systems that no matter which region you're looking at or what type of market construct might be in that area, what are 6 principles that really apply uniformly across the system? We want to take a really high level view, not get specific to any jurisdictional or regulatory framework in a specific region, but again, set something that can be used across the industry. And so we came up with these 6. I won't go into these in huge detail. I've spoken at a couple resource adequacy, ESIG events on these, and then also have the white paper that covers it extensively. So I will touch on each of these though throughout the presentation. So the second topic, that kind of sets the framework of how we're thinking about resource adequacy. And now want to shift gears and talk specifically about the weather, because as I alluded to in the last few slides, weather is fundamentally a driving force for resource adequacy, and only become increasingly so as the system transitions towards a decarbonized future with increased renewables and storage. And so one of the key principles is chronological operations must be modeled across many weather years. This is key. It's not just modeling a single year of sequential modeling and 8760 modeling, but doing it across many weather years. And I have two images here of the weather during the California and Texas event. What was true about both of them, they were large region-wide or large swaths of the United States wide weather events. So in the California example, there was a heat dome across the entire Western US. We saw that again this past year, although thankfully resource adequacy was maintained throughout. And then in the Texas event, again, the entire middle of the United States, ERCOT, SPP, MISO, all seeing historic cold snap. The other thing, both of these events were well outside our kind of normal planning framework in terms of, I think California was a once in a 30-year heat wave. Again, back in 2020, I think we broke some records this past year, if not in California, then in other parts of the West. And then in Texas, it was a once in maybe 50 or once in 100-year cold snap that hit there. So again, outside of our normal planning framework, but something that we certainly need to keep an eye on. Is the historical record still the appropriate one to use for future planning? And the key thing here is, again, going through these weather years sequentially, making sure we're getting a wide degree of variability, not just on the wind and solar resource, which I think that the industry has done a pretty good job at capturing over the past several years, but also on the temperature data that's underpinning our load and generator forced outage rates for the gas fleet, and then also on other weather conditions that could, again, disrupt potentially the gas network and heating demand overall, and the linkages between those sectors. And again, all hours now start to matter. It's not just these peak load conditions. It's not just the summer peak snap that's going to catch the system short, and our risk is starting to shift to other seasons and other times of the day. So this is a figure that we just put together for some work with Grid Lab, looking at California in a very high renewable portfolio, so up to 85% clean energy, and a large portion of that coming from wind and solar. We looked, this is a figure across 8 weather years. We have some data that extends it out to 20. But we looked at the variable renewable energy, wind and solar, as a percentage of daily load. Because again, this is a future system with a lot of storage on the system. So we're not as concerned about hour-to-hour fluctuations in the resource because we have so much storage on the system. But again, the day-to-day or multi-day events. And when you look at the data, this is, again, very California-centric, but we have a scatter plot here of percentage of daily load served by wind and solar across 8 weather years. The gray dot is each individual day, and so you see somewhat larger spread. And then the blue dot is a 3-day rolling average. So again, trying to capture these multi-day events where you have 3 consecutive days in a row with low wind and solar. And you can see there's some outliers at the bottom of this chart. All of those are in the winter. So that's notable, right? In the summer, especially in a really high solar grid, there's going to be ample amount of solar energy, even on a cloudy day, and certainly with the longer daylight time period. But in the winter, that's when these winter storms can come in, not only have lulls in wind production, but also in reduced solar output. And again, in California, not as much of an impact on heating demand, but as you get to other regions and see similar phenomena, you see also a corollary on the heating demand, both for electric heating in places where there's electric heating, but also on increased demand for gas supply on the gas network, which has competing use cases between building, heat demand, and power generation. So again, the risk is starting to shift. We see these winter events being a potential increase in reliability risk, Obviously, that played out in Texas because of systemic failures on the gas supply network and other aspects. But certainly, as we start to electrify our heating and rely more on variable renewables, not just for energy, but for capacity, we are likely going to see a shift towards reliability risk, inching away from just that summer peak load period and into the winter. And so this is a chart that we adapted from some work that E3 did that I think very nicely illustrates this transition of the reliability challenge. And historically, all of our reliability challenge was concentrated on that peak load period. So in a system and grid with conventional fossil fuel fired generation, and this idea that risk is mostly uncorrelated on those failures, we see the peak load tended to be the highest period of risk. And in most places in North America, that was summer. When you get into the Pacific Northwest and the Southeast, you see peak demand periods also occurring in the winter. But today, in most places, especially places with a lot of renewables, we see the peak risk for reliability or resource adequacy shift towards the net peak. And so this, in a solar-centric region, is shifting the risk a little bit later in the day into the evening hours after the sun sets. In a wind-centric region, maybe it shifts it from the peak demand week to a week on either end that maybe had similarly high load but low wind production. So that's kind of where people are grappling today. A lot of the places you see resource adequacy work being done or changed and different programs being put in place, it's really to capture that shift to the net peak. So right now, a lot of work being done in California on their resource adequacy redesign program on how to better capture reliability specifically at different time periods of the day. We'll get into that in a little more detail. And then lastly, you see the orange line, as we start to approach a renewable grid, approaching very high levels of renewables, approaching 100%, there's really this increasing winter challenge that we start to see. And this is periods of highest risk are now going to be during periods of lulls in potential renewable generation, periods where the gas supply network is also strained, load maybe not as high as summer peak conditions, also high and increasing because of electrification of heating demand. So certainly something to keep an eye on. Obviously, a lot of people today focusing on that net peak challenge, but I think that the challenge of tomorrow is the winter challenge. So it's different seasonal approach. It's also a multi-day potential issue where you have multi-day consecutive periods of low wind and solar. And so that could have implications on the type of resources that we need to be planning for, again, as we push out to very high levels of renewables. So where are we today? I've put together, it's a little bit of a cartoon, but a power industry weather modeling report card to really take a step back and say, if all of our resource adequacy is dependent on the weather, we need better weather data in our power system modeling. And kind of where we stand today is a pretty wide spectrum. And so going down the list here, solar data in general, I think the industry has done a fairly good job. We have long periods of historical record. I always point to the NREL NSRTB as a really good data source for solar production. Any place in the country you can pick a spot on the map, it'll give you 22 plus years of hourly solar production data. Correlates pretty well to actuals as far as I've seen. And so we have this really nice, consistent data set anywhere in the country you can pick, and you can get time series of solar data. Certainly more we could do. We could extend weather years out a little bit. Probably more work to be done on these outlier storm events and extreme weather events. But in general, solar is doing okay. On the wind data side, I gave that a C+. And the big one for that is just the amount of available data that we have, the years of historical record. We just don't have that same broadly available nationwide data set for 22 plus years of wind data. So I think we made a lot of progress. Certainly any individual region, I know folks, ERCOT has done a great job getting a 40-year data set for both wind and solar, and I'm sure other places have done similar work. So improvement to be done there. Again, one thing that's important is making sure that the solar and wind data is in our modeling is from the same source. We're we're capturing the same meteorological conditions for both data sets. Not just that we're modeling 2018 data, solar data with 2018 wind data. We want to make sure the underlying data source is consistent as well. So I think that's something that can be improved. Load data, gave that a B. Again, we have a long historical record. I think there's been a lot of industry experience over the years on how temperature and weather data influences load. So overall, fairly good. I think it's becoming increasingly challenging as we start to integrate more DER. So the load itself is kind of a function of the underlying weather. It's one of the reasons why I typically propose modeling the DER as a supply side resource in some of this modeling, is to make sure we pick up on that weather dependency. But then you see the bottom half of this report card, the wheels start to fall off. So temperature data, we don't do a great job as an industry capturing temperature dependent reliability risk on thermal generators. If you look at the data, especially in winter cold snaps, you have much higher forced outage rates of the underlying thermal fleet than you have across the rest of the year. So, upwards in ERCOT, in MISO, PJM, and recent cold snaps, you saw outage rates that on average across the year, maybe 6 or 7% on some of the thermal fleet, exceeding 30, 40% and being pretty consistent across multiple cold snaps. So I think that's something we can improve. The last one that also influences the gas-electric coordination. So now the weather dependency not only affecting the fuel supply on the power generation, but also leading to a spike of fuel supply needs on the heating demand. And so the interaction between the coordination between gas and electric sectors, I put an F there. One of the big reasons why there is challenge in the ERCOT event in February of last year, and yet most of our modeling, is, and mine included, would not pick up on that risk because we're not getting that cross-sector coordination. And then lastly, climate trends. I think people are starting to recognize this as a challenge, but still a lot of disparity in how we implement that in our resource adequacy modeling. I gave it a C-. Really, the only reason it wasn't worse is because the importance, I think, of these top items outweigh currently the climate trend. I think that's a longer term trend that we can continue to adapt, and maybe it's new for everybody, so we won't grade people so poorly. A little bit of a cartoon, to walk through this. I put some other comments about, in general, we do a really poor job working with others, especially interregional planning. And I'm coming at this a little bit for this report card. This is North American or US centric. If you look at what's being done in Europe, in NSOE, in their resource adequacy framework, I think they get better marks across the board on this in terms of having a consistent weather data set underlying the analysis and really doing a much better job at interregional coordination and doing a pan-European assessment. I think that's something we can really learn from. So, I think this is something I've targeted as an ideal next step for the industry to tackle, and certainly a place where ESIG can help. What do we do to fill these gaps? The truth is we have imperfect weather data today. We kind of know what that ideal data set looks like. It's a time synchronized weather data set covering solar, wind, load, temperature across both electric and gas, and it includes climate trends. That's a huge wish list, right? And certainly we don't have that data set today. So what do we do to fill the gaps? And this is where reviewing resource adequacy works across the country. This is where I've seen a huge disparity in the way people approach filling the gaps. And there's no great playbook on how to do this. So everybody's kind of working through these challenges themselves. And so I won't say that anybody's doing it wrong. It's just we have imperfect data. People are filling the gaps. You see folks bootstrapping data sets, and maybe they have 4 years of data, historical data, and they say, well, I know I need 40, so maybe I correlate it to temperature or something like that. And I come up with a synthetic 40-year data set. And certainly limitations to that. You'll see folks repeating data, see other people just straight guessing. So I think there's a real need, and again, an opportunity for ESIG to come in, not just say, what weather data do we need, although I think that's important, but also in the meantime, what are some best practices on filling those gaps? And so for this, I think there's really a need for, again, cross-disciplinary. With the power systems engineers are not going to be able to solve this on our own, and the atmospheric science folks don't have the background in power systems. So we need cross-disciplinary work here, and it needs to be inter-regional research. So again, as we rely more on variable resources and the geographic diversity of both load and the supply, it becomes increasingly important. We need to look at this not just in one regional footprint, but inter-regional. So I'll touch quickly on metrics before I get into the next section. Again, I think this was the topic of my fall ESIG technical workshop presentation. So if you want to learn more, there's a whole presentation devoted to this slide. And again, the C-grade paper that we're going to be putting out later this year is going to focus on this. But something you'll hear over and over again when you hear me speak, and again when you read the ESIG report, is quantifying the size, frequency, duration, and timing of capacity shortfalls is critical to finding the right resource solutions. So if you look at the way we do resource adequacy planning today, most of us will rely on something like loss of load expectation, which counts the number of days per year where we have a shortfall. And it's an average. We run hundreds of different simulations, and we say our LOLE, we want to get it as close as possible to 0.1 days per year, or 1 day in 10. Europe uses a loss of load hours, so just hours per year metric predominantly, not uniformly. But those metrics, certainly do not quantify frequency, duration, and timing. And so we need to go further with our metrics. And I've showed that here in again, comparing the California and Texas events. If you look at it from a loss of load expectation, either in days or events, the events don't look that different. When you start to use loss of load hours, you start to see the two events differentiate, but it's not until you get to an unserved energy metric, or EUE, expected unserved energy, that you start to see the disparity. And again, used EUE here because in megawatt hours, I think that's something we're all accustomed to. There's normalized EUE, which is a percentage of load that could also be used. California and Texas, certainly not the same size, but they're not too far off that this order of magnitude is pronounced. So again, making sure we have metrics. If everything I'm saying today is we're shifting to relying more on variable renewables where the energy is uncertain and energy limited resources like storage and demand response, if fundamentally we're becoming more energy constrained, making sure our metrics reflect or quantify our shortfall in energy, like EUE, I think that's going to become increasingly important. So the 4 recommendations, one is place more emphasis on expected unserved energy. The second is we don't have to just use one. So most folks today use, again, in North America, a 1 day in 10 year loss of load expectation. We don't have to be wedded to that. We can continue to use it, but important, we have a suite of metrics. We can use them both in our reporting, but also in our reliability criteria. The other thing with these metrics, they're all expected values. We run hundreds of different simulations, and we take an average metric, and we say our loss of load expectation on average is 1 day in 10 years. Well, what about the tail events? What about what happened in ERCOT? Should we be looking not just at these averages, but looking at tail events? Expected unserved energy will help in that sense because it'll implicitly weight the larger events more. But I think we can, again, look at things more on a distribution. And then finally, when we have a shortfall, what does that shortfall look like? And I think this is certainly where resource adequacy analysis can improve the most. It's something we can do very easily today, is just drill into the individual shortfalls, not the average total amount in a year, but when we have a shortfall, what does it look like? And that's important because, historically we had a one-size-fits-all approach to solving resource adequacy, right? Basically the combustion turbine was the default reliability mitigation when we had to design a system to meet a 1 day in 10 year loss of load expectation. And when we had kind of that one-size-fits-all, that we had one tool in the toolkit, it didn't really matter how the duration of those shortfalls, it didn't matter how much energy was unserved in those shortfalls, because we had because all we have is gas turbine. Today, we have a lot more mitigations available in our toolkit. We have storage that comes in all sorts of different varieties, different durations, different chemistries. So we need to know, again, more about the underlying risk. How long are the events? How much energy is being shed? And again, on load flexibility, same thing. And so this is a chart that shows of all the loss of load events, kind of ranking them or putting them into a bin based on their energy shortfall going down the rows, and then the power shortfalls going around across the columns. And when you do this, this is on a fairly small system, but when you do something like this, you'll notice, especially on the current system, most of the events tend to be very short duration events, maybe 1-2 hours. And you can really start to right size a resource. You can see here, 70% of the events covered by a 60 megawatt 2-hour resource, or 85% by a 100 megawatt 2-hour resource. And when you frame it in that context, it's very clear that there's certain mitigations that meet the reliability needs. And you don't need a resource necessarily that is available every hour of the year to be resource adequate. And so certainly that will change over time as the amount of renewables on the system changes, as the amount of energy limited resources change, but something that we need to be able to track. And that kind of takes me to my last point on capacity accreditation. Probably won't be able to get into all of this given the time, and certainly want to leave some time for questions. But how capacity accreditation is how we measure these resources. Again, I said we have all different resources available in our toolkit now. How do we measure them against one another for the resource adequacy benefits they bring? And so fundamentally, that's capacity accreditation. And the way I frame this, I put together a very simplistic cartoon here, but it illustrates the way I'm thinking about capacity accreditation. So on the one side, we have our resource adequacy analysis that everything I've talked about today is how do we measure whether or not the system is reliable? And so that's our loss of load expectation, it's our expected unserved energy, it's the probabilistic assessment that's measuring the resource adequacy of the system. It's saying, is the portfolio we have reliable or not? It doesn't necessarily directly help do the resource procurement, which is making sure we can purchase the right capacity in the right places at the right time. And purchasing capacity is one way if load is growing. The other way to look at this is retiring capacity. Is there surplus capacity on the system? How do we make those retirement decisions? So fundamentally, resource procurement. Now, we need a bridge to get us from resource adequacy to resource procurement. And today, that bridge is the planning reserve margin and effective load carrying capability. It's worked very well in the past. I'll say, as you can see from the cartoon, you can understand where my thinking is today. I think that bridge is fundamentally eroding and becoming weaker and weaker as the system transitions. So we need to rethink the way we come up with kind of bridging this gap between resource adequacy and resource procurement. And again, today, how we do that is the planning reserve margin. And my thought here is the planning reserve margin has really outlived its usefulness for power system planning. There's a lot of reason for that. The risk, again, is shifting away from these non-peak periods like we've discussed. It relies on effective load carrying capability analysis to remain credible, and I'll walk through a couple of issues there around saturation and portfolio effects. Storage makes the system energy limited, not necessarily capacity limited, and so planning reserve margin is just stacking up different capacity. And then the thermal units, again, the assumption was we know that thermal units have correlated outages, and we can't just stack up unforced capacity or a thermal unit's capacity minus its forced outage rate. So we know from experience that is increasingly challenged. And so here, this is, I put a link to Gord Stephen. Gord is on this ESIG Redefining Resource Adequacy Task Force. He did a great job talking about kind of the limitations of the planning reserve margin and why we have to think about it differently. So today, we have, in this, I'm going to take his full presentation and simplify it into three quick images here. Today, we have our demand that fluctuates over the year, and we take that peak demand and we add a planning reserve margin, and we say if we can cover that peak demand period, we can cover the rest of the year. And with conventional thermal resources, that was an okay assumption, right? You had these resources that were uniformly available over the year. Maybe you had to worry about outages occurring, but you could stack it up, and because they're uniformly available, if you could meet that peak demand period, you could also meet the rest of the year. And then we shift to a high renewable situation, and here you can see now our resources are not uniformly available. They're fluctuating based on the weather conditions and just overall resource availability. And you can see here is an example where the system was more than adequate during that peak demand period, but now with a lull in some generation, you see a shortfall in this hash period that occurs. Again, the risk shifting outside of that peak demand period because the supply mix is changing. And certainly, Gord does a great job going on in this presentation to show how even when you add storage to shift energy from one time to the other, you have to start taking into account these storage constraints. And so really a fundamental need to move beyond the planning reserve margin. One other point I want to make about the planning reserve margin, I said it fundamentally relies on effective load carrying capability. So that bridge that spans us from resource adequacy analysis to resource procurement decisions required kind of planning reserve margin to stack up resources, and ELCC to say, well, we know not all resources are created equally, so some have more ability to meet those peak demand periods or those peak risk periods better than others. And so we use effective load carrying capability to measure that the ability of resources to provide that firm capacity. And this has been used widely across the industry for many, many years. And it worked really well for renewables at early penetration levels. But we're starting to see what a lot of the work today is focused on is two things: saturation effects and portfolio effects. So saturation effects, we know the capacity value of a resource decreases as its installations increase. So the more and more solar, storage, wind that we put on the system, the incremental capacity value that those resources bring diminishes as the installations increase. And the reason for that is, one, reliability risk shifts to different periods, or the reliability risk gets flatter, right? If we clip off those peak load periods, the remaining risk just gets spread over longer periods, so storage duration requirements have to go up. And then again, you're not only limited on capacity, you're limited on energy available to charge our resources, charge our energy storage resources. So for all those reasons, kind of as we start to incrementally add resources to the mix, the capacity value diminishes. But it's not that straightforward. So we had a lot of experience as an industry working through those saturation effects, especially on wind and solar, and over the past couple of years have gotten a lot better on storage. But there's the portfolio effects as well. And E3 has done a lot of great work kind of illustrating the portfolio effects. I know NREL has also done some good work here, where the capacity value of one resource depends a lot on all of the other resources that are on the system. So the capacity value of solar depends on how much storage you have. It depends on how much wind you have. It also depends on the underlying load profile. All of these things are changing as we go out in time. And so because of that, it's a constantly moving target. And fundamentally, these portfolio effects make it really hard to do this forward-looking analysis on ELCC. Not that it's impossible, it just becomes increasingly difficult. And the saturation effects, here, just an example from some Brattle work in New York. You can see for storage, onshore wind, offshore wind, and solar, both in summer and winter, you can see the diminishing capacity credit afforded to resources. And again, on the portfolio side, some work done out of E3, again, that explains all of this in a lot more detail. You can see there's synergistic benefits between different resources. So solar by itself will clip or push out the peak demand risk to later in the evening and kind of has some capacity credit. Storage can do the same thing, but when you put the two together, the solar, there's two benefits. The solar is making the peak load, evening load period narrower, which makes it an energy limited resource, so the duration need also lower, and it also provides surplus energy for charging the resources. So you can see you get these portfolio benefits of the resources put together in tandem. And so again, this is work coming out of E3. They developed the delta method to be able to take this portfolio benefit. So again, the combination of our renewables and our storage together provides more reliability than the incremental benefit of any one in isolation. The question is, how do you capture that? And so it's kind of analogous to the cost allocation challenge in transmission planning, where you have these benefits, and the question is, how do you proportion them out to different entities? And so the same thing happens on our diversity benefit from ELCC. How you proportion out that portfolio benefit to the underlying resource gets really challenging. And again, as we look into the future, there's more uncertainty in not only how much of an individual resource is on the system, but of all the other resources. So certainly getting more and more complicated. And then lastly, what I want to talk about is, one of the other underlying principles is there's no such thing as perfect capacity. And I've talked a lot about the systemic risk in both gas supply and temperature-related outages on thermal capacity, and making sure we get that in our modeling correct. So we have highly correlated outages, ambient derates during extreme temperatures, fuel supply risk, and cross-sector dependencies on the gas network. I think we need to go one step further and start applying these capacity accreditation methods to other resources on the system. Otherwise, I mean, fundamentally, not only is there a potential equity concern between different resources, which I think is worth discussing, but more importantly is, if we don't do this, we're going to keep showing there's summer reliability risk, which there is, but we're going to completely miss this transition to potential for risk shifting to other time periods, most notably the winter. So I think something we really need to think harder about. And lastly, there's some other folks doing some work on an alternative to the planning reserve margin. So I highlighted too here the Pacific Gas and Electric slice a day, which is broadly being discussed across California right now. And then in Hawaii, the energy reserve margin, which looks at, instead of a planning reserve margin on peak load hours, it's looking across an entire day, or sorry, an entire year. I won't go into any of those in detail, but certainly, it's no surprise that California and Hawaii are the ones that are really grappling with this challenge today. I think we can look to them as kind of the folks pushing the frontier on the renewables, as if they're seeing a challenge here, chances are the rest of us will too. And just for a framework, and another way to think about this from a planning perspective is, historically we used the planning reserve margin and ELCC as an input into our capacity expansion planning process. So some work we did with HNEI, we developed kind of an iterative framework to say, well, what if we do the resource adequacy analysis after, and we make this an iterative approach. So you get a portfolio, you run it through the resource adequacy analysis, and then you iterate back. You can adjust your reserve margin requirement. You can use the size, frequency, duration, and timing of shortfalls to get the right capacity addition, and you can tweak that capacity expansion plan. I think in the meantime, this is the route we have to go for long-term planning. And then obviously, that's not the only things we need to think about for reliability. There's kind of full production cost simulations to get the balancing, and then stability simulations as well. So just to wrap up, next steps for resource adequacy, I think new metrics, I pointed that out. I think there's a lot of work that can be done on capturing those new metrics in different regions and calibrating them. Best practices around weather data and improving that. And lastly, capacity accreditation alternatives and moving away from that planning reserve margin. All three of those, I think, are ripe for future research. I think ESIG is a great place for a lot of that to happen, and look forward to helping with that discussion. And with that, we'll switch over to Slido.
Okay, Derek, thank you. I think that Derek has really hit us with a bucket load of information in the last 10 minutes. There's a lot of a lot of unrated questions that came in on Slido in the last 10, 15 minutes. So if you're want to move some of those up to the top, go ahead and vote on some of those, and we'll take a look at what's come in so far. There's one question, I think, based on your observations at the end about peak winter risk and the common mode failures in thermal plants. I'm going to move down to I guess it's the fourth question there. Is there any research, any information or research available to correlate thermal generation outage rate with weather? Very related question.
Yes, I have a couple, citations I can provide on that. I think there's more and more work being done in this space. So I can maybe follow up with a few citations via email. In the ESIG white paper, we do have a chart that shows, again, specific events, what the outage rate was in MISO, PJM, and ERCOT in recent cold snaps. So I think 4 recent cold snaps, we show the average forced outage rate that folks are using in their planning, and then what actually occurred during those events. Those are event-based, and then there's also a lot of work being done kind of pouring through NERC data and getting accurate forced outage rates based on temperature. So certainly I can point to a few links on that.
Okay, maybe we can include some of those in the question and answers that we send out after the webinar also. One from Russ here that's moved up to the top pretty quickly. What are appropriate mechanisms to pay for resource adequacy? And then a list: capacity markets, energy only markets, operating reserve, demand curve, real-time payments, bilateral contracts. Any thoughts on that?
Yeah, I think I have a lot of thoughts. I'll try to go quickly. On capacity markets, I think there's going to be a constant struggle in the mandatory capacity markets that we see in ISO New England, PJM, and New York ISO, where because it's a kind of liquid market and we need to buy and sell a commodity, essentially, it's going to require us to commoditize the resource adequacy capability of every generator. And so that's where ELCC comes in. I kind of touched on some of the challenges and limitations of ELCC in the future. Fundamentally, it's needed in the capacity market construct because we need to be trading commodities, and that's the way we can take all this different type of generation and try to put it on somewhat of a playing field so it can be kind of bought and sold in uniform blocks. Like there's a desire to stack blocks up until we hit a capacity market requirement. I think fundamentally that ability is starting to erode or will erode over time. Energy only markets, if we have rational actors and folks are hedging energy only risk, I think there's an opportunity there. The economist in me likes that approach, but I think we've seen failures there and some challenges. And lastly, like bilateral contracts, and really where I think some of this will go outside of the mandatory capacity markets is load serving entities are going to have to bring a portfolio of resources to the table that can be measured for region-wide reliability capability. And I like that approach because, again, it allows a load serving entity to bring a portfolio. You get the portfolio benefits of that capacity accreditation. And it allows folks to bring the resource portfolio that they want to bring to the table. And then you can measure the reliability it brings relative to all the other loads doing the same thing. And you can end up with kind of, you can test the system, you can identify shortfalls, and then cost allocate the benefits. So I think there's kind of going to be a trend in that direction, but we'll see if that pans out.
Okay, and one on progress out there, Derek, are there any regions that have successfully shifted away from the old planning reserve margin way of assessing RA?
Yeah, I think that's what I tried to allude to here in the last couple slides with pointing to California and Hawaii. I think both in the process of moving in this direction. But yeah, this is fairly novel. I think both of those places have introduced these PRM alternatives in the past year. So I think certainly something we will see more of, and then whether or not when we'll see folks being successful, I think it's a trend that will continue and we can get there.
Okay, next one, kind of a follow-up on the earlier one on thermal. Since thermal units represent the majority of capacity, Can you expand on what capacity accreditation methods ISO should apply to thermals?
I think for now, if we're using ELCC across the board, we can use something similar for thermals, provided that we're capturing the increased forced outage rates with temperature correlation, and provided that we're getting the fuel supply risk embedded in the modeling. If we don't change our underlying modeling, we're not going to do anything on the capacity accreditation side, right? The capacity accreditation all depends on robust resource adequacy modeling. So I think we have to get that right first. We can then apply it to thermal units. And then also, fundamentally, what we'll see that do is potentially shift risk appropriately, at least quantify risk in the winter season. It'll also provide a signal for dual fuel capability, which right now we don't have many market-based incentives to get generators to have dual fuel capability, when I think there's a reliability benefit of that. So I think having ELCC as a way to differentiate resources with dual fuel capability is important.
Let me take a follow-up question, Derek, that's related to that one, just a couple below. Are you suggesting states should adopt resource planning processes that meet requirements for a suite of metrics? And should the RTOs have requirements for these?
Yeah, it's a good question. I think, first is there are places that are starting to consider dual use metrics. I think the Pacific Northwest has put out some ideas on dual metrics. Some work in Belgium has dual reliability criterion. So there's potential for it to go that direction. I'm not sure we necessarily need to go to a dual reliability criteria right away. I think the first is just to report them on a consistent basis and keep track of them. So if 1 day in 10 years remains the criteria, at least show, is there a change in expected unserved energy or loss of load hours that's happening over time? Because you'll see that they are not necessarily linearly correlated. And then lastly, on dual criteria, we could always just shift to an alternative criteria like expected unserved energy, which I think over time we'll need to do because the system's becoming more energy constrained. But again, I think a lot more work has to be done on how we calibrate.
Okay, there's a lot of really good questions here, Derek. One here on the database. Are you aware of any groups that are organizing or culling publicly available weather data for use by the research community? Lack of data remains a big problem, which you pointed out.
Yeah, there's certainly places that will cull publicly available weather data. The challenge there is, are you using consistent weather data across the different data sources? Are you modeling wind with a consistent data source as solar? I don't know of anybody kind of providing that consistent data source. And then on the load side, we have historical loads pretty well captured, but making sure that's linked to weather, big data gap there. And if somebody else knows of other folks doing that, would like to.
Okay, I want to get in this question from Australia, since our Australian colleagues got up early in the morning to listen to this. We're currently working on designing a capacity mechanism for the NEM in Australia, the National Electricity Market. Which international capacity markets best handle these emerging risks? Got any thoughts there, Derek?
Oh, man.
Designing a capacity mechanism for the NEM.
Yeah, I think, the capacity markets in the Northeast are working through ELCC accreditation and making a lot of improvements there. Still work to be done that I highlighted. The Pacific Northwest is putting together a new resource adequacy framework. And I think does a good job of opening up the door to bilateral trading and consistent accounting across all the different VAs in the West. So I'd highlight that, although it's probably not as relevant for a single market in Australia. I'm trying to think of, and then kind of what I would make kind of throw in the same bucket of California, MISO, SPP, all having these reliability requirements. Folks kind of can bring their own capacity portfolio to the table, and then there's a reliability backstop. I think that reliability backstop or capacity market as a backstop is a unique approach where we kind of allow folks to bring the portfolio they want to bring to the table, and then there's a backstop auction or capacity market that can fill in any gaps. I think that's a unique approach.
Okay. I'm probably going to run over just a minute or two, but these questions are so good, I just have to ask them, Derek. Here's another one from Russ. Reliability depends on balancing immediate and future needs, particularly with storage. Isn't there a role for RA in operations, not just long-term planning?
Yeah, certainly. I think, in that policy brief we just put out for ESIG and GPST in anticipation of COP, we have kind of this spectrum of kind of resource adequacy going from hours ahead all the way to decades ahead, and all the considerations that get layered in. And there's the policy framework and the planning framework that goes from 5 years out to maybe 20, and then there's resource adequacy season ahead, like all the ISOs do their seasonal assessments. But certainly there's as we start to get to these multi-day events, you can start thinking of it also as days out. I think, Russ, you bring up a valid point. As we start to increase the amount of storage on the system, the ability to forecast not only the weather resources, but forecast the storage utilization is going to become more and more important.
Okay, the last question I want to take, Derek, I want to expand the discussion just a little bit and take this one from Nick.
Yep.
Can you discuss transmission as a resource approach, i.e., how the addition of transmission can be brought into the decision-making process of capacity addition?
Yes. So I would, and this is fleshed out a little more in that ESIG white paper, but fundamentally, I view transmission as having capacity benefits the same way a supply-side resource has it. So right now, being able to shift energy or capacity from one region to another will have a reliability benefit. We can capture the geographic diversity in the underlying resource. We can capture it in the underlying load. And so anytime you have, I look at it as a small balancing authority that can share resources with a neighbor and there's a way to do that without even increasing the transmission capability on the system. So that's one way to look at it, just inter-regional coordination. And then if you do that to a point where you're hitting up against transmission barriers, then going forward and viewing transmission as a capacity resource. And so basically modeling it as either a way that reduces the kind of planning reserve margin or reliability criteria, or as kind of providing ELCC capacity to the system, either way. So the answer to Nick's question is yes, we should be evaluating transmission as a supply side resource.
Yeah, thanks. I want to thank you for bringing that point up. I think it's really an important part of the resource adequacy conversation. Well, we're a little past the top of the hour, so we're going to need to wrap it up. Derek, I really want to thank you for this informative presentation. I hope everybody found something to take home. I know I certainly did. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to. And there's a lot of good questions there, and I want to thank Derek again for doing that. And we'll get them posted as quickly as possible. We appreciate everyone's engagement. Look forward to seeing you again soon at our next webinar on November 30th on the GPST research agenda for the founding system operators. We hope you'll be able to join us once again for this or another one of our future events. Further information on all of our webinars and meetings can be found on our website at esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. Derek, thank you once again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.
Thank you all.
Thank you.